Hi, do you want to know what is new in MICROSAR Classic with release 36? Well then, just stay tuned. I'm Andreas Wenkebach, Product Manager for MICROSAR Classic, and I hope you will enjoy my topic selection. Now, this is what I'm going to present. There is DCA Remote UDA, a generic and central approach that allows to configure your data collection use case. With release 36, we started to offer a specific FEE component for eMMC memory. We continued our development of PQC algorithms and now are more complete in our offer. For USWC development in Rust, we offer RTE Support. We continuously improve performance and code size of our stack. With release 36, we applied a lot of improvements specifically to the FiM component. A highlight in release 36 was precision enhancement for Ethernet global time synchronization. An innovative SaaS-based tooling now is offered to automatically do NVRAM endurance simulation for you. A quite big feature in release 36 was Wake on Dataline, following AUTOSAR 2311. A short update only on the topic I presented in my release 34 spotlight. Our new gateway solution offering routing on a dedicated core for maximum performance is now available in QM. And a short remark, as usually you find the complete release information in the release notes provided with your delivery or from our vector portal. Let me introduce to you DCA Remote UDA. So why did we introduce it into the Classic platform? OEMs are asking for much deeper insights into their ECUs, not only in development vehicles, but across test and series fleets. Traditional lock and trace mechanisms are limited. They are coarse-grained, text-based, and hard to control selectively. This is exactly where data collection comes in. The DCA Remote UDA allows us to collect structured ECU data efficiently and with minimal CPU and runtime overhead. So how does that work? Technically, the approach is polling-based. All potential data points are defined upfront, but they are activated and configured dynamically at runtime, either cyclically or on request from the backend. The key difference to lock and trace is the data itself. We collect native structured data points, not free text logs that need post-processing or interpretation. So what did we achieve so far? Data points are connected via generated callouts to existing classic BSW modules. And many standard data points are already provided out of the box. Currently, we support to send out the data via VDP protocol only. The data is forwarded via VDP, CM remote, and PDUR to the data collection core on the HPC, and from there into the cloud. This enables continuous optimization even when traditional loggers are no longer available in the vehicle. FEE for eMMC. Why do we need a dedicated FEE solution here? eMMC, or Embedded Multimedia Card, is a managed NAND technology that is increasingly used in modern ECUs, especially when large non-volatile memory is required at low cost. Unlike raw NAND, eMMC already handles many hardware-specific aspects internally, such as wear leveling, bad block management, and robustness during resets. Existing FEE solutions were designed for raw NAND flash and cannot be efficiently reused for eMMC devices. Re-implementing NAND emulation in software would add unnecessary complexity and overhead. This is why we introduced a dedicated FEE solution, optimized for eMMC. Our approach is to leverage the hardware capabilities of the eMMC controller, instead of compensating for them in software. As a result, the solution has a reduced footprint, is robust against resets and power loss, and integrates seamlessly with the existing vector memory stack. For our customers, this means a reliable, production-ready NV storage solution with lower complexity and integration effort. A beta version is already available with release 36. QM is currently planned with release 37. In release 34 Spotlight, I gave you already an overview on our PQC algorithms we implemented and planned at the time. Let me give you an update on what we now did in release 36. So as a short recap, why are we talking about post-quantum cryptography in MICROSAR? Well, today's classical asymmetric cryptography, such as RSA, ECC, Diffie-Hellman or ECDH, will be broken soon by quantum computers, most probably. According to estimates by National Institute of Standards and Technology, or in short NIST, this becomes relevant in the time frame from around 2030 onwards. In automotive systems with very long lifetimes, this means we need to prepare much earlier, so best already now. To address this, NIST has standardized a new set of post-quantum cryptographic algorithms based on hard mathematical problems that are not vulnerable to quantum attacks. The selected algorithms include ML-DSA for digital signatures, ML-KEM for key exchange, and SLH-DSA, a stateless hash-based signature algorithms. We are integrating these algorithms step by step into MICROSAR Crypto software stack and MICROSAR HSM stack. SLH-DSA with SHA-256 at security level 128S is already supported in QM today. Later this year, we will provide beta versions of ML-DSA 65 and ML-KEM 1024, followed by QM releases towards the end of the year. This allows our customers to start their transition towards quantum-resistant vehicle security well ahead of real-world quantum threats. Why are we talking about generating Rust code from RTE? Rust is gaining strong momentum in the embedded and automotive industry, mainly because it provides memory safety by design. It prevents common issues such as null pointer access, buffer overflows, and many forms of data races. Problems that are difficult and costly to fully prevent in the C programming language. With release 36, we enable a safe way to bring Rust into MICROSAR Classic applications using the RTE. The key idea is that RTE becomes a language-aware abstraction layer, not only between basic software and application, but also between C and Rust components. Each Rust runnable receives an RTE parameter that exposes only the APIs that are valid for the runnable. This means developers cannot accidentally call APIs from the wrong context. The IDE simply does not offer them. This significantly reduces the risk of data races and memory access violations, while keeping the familiar AUTOSAR structure. The RTE generator produces a structured Rust setup based on crates. One crate provides the system interfaces and data types, while another contains runnable bodies and user code sections. The feature is currently provided as beta. Not all RTE features are available yet, and the solution is not production ready. Based on customer feedback and adoption, the feature set will be extended and qualification towards QM or ASIL will be considered in future releases. Like already mentioned, we continuously improve our MICROSAR Classic stack in both performance and code size. With release 36, we introduced two FiM improvements that significantly enhance performance. The first improvement addresses how fit status changes are handled. Traditionally, applications rely on cyclic polling to monitor FiM status, which causes unnecessary CPU load and delays. With release 36, FiM now provides an optional callback mechanism. Instead of polling, the application can be notified directly when a fit status changes. This callback-based approach acts as an alternative to cyclic polling and leads to a significant reduction in FiM-related CPU usage. The second improvement targets multi-core systems. Previously, fit status calculations were handled centrally by a FiM master core. In Release 36, the calculation can now be performed on the same core where the application requests it. This distributes the CPU load across cores, reduces dependencies between master and satellite cores, and improves FiM reaction time for status changes. Both features are optional in order to remain downward compatible. Existing configurations remain fully supported, while new configurations can directly benefit from these performance improvements. With zonal architectures and Ethernet backbones, time synchronization faces new challenges. Precision requirements are significantly higher than before, and time synchronization is no longer a local topic. It spans the entire vehicle network. At the same time, safety and reliability are mandatory, and new hardware-driven use cases depend on a highly precise global time. With Release 36, we introduce a precision enhancement for Ethernet global time synchronization. The key change is that the hardware clock itself is now synchronized directly. The global time is corrected inside the physical hardware clock, instead of being calculated and converted in software. This significantly reduces jitter and allows multiple consumers, even across cores or partitions, to access the same precise global time source. This also enables new hardware-based use cases, such as timestamping based on global time and fine-grained precision calibration using the PPS pin. In addition, we enhanced safety and reliability. Based on AUTOSAR-2311, time synchronization can now be validated and monitored system-wide, with ECU-specific supervision and defined fallback handling to reach safe states in case of errors. Overall, this feature prepares Ethernet-based vehicle architectures for high-precision, safety-critical time synchronization. So with this slide, I'd like to introduce NVRAM endurance simulation, now available as a software-as-a-service offering. Why is endurance simulation needed at all? Well, flash memory has a limited number of write and erase cycles. To extend its lifetime, techniques like wear leveling are used, typically handled by the FEE module. However, the actual flash endurance strongly depends on the FEE configuration and its runtime behavior. If the memory stack is not configured optimally, this can lead to reduced hardware lifetime, unexpected behavior, and eventually integration or performance issues later in the project lifecycle. Until now, many teams lacked clear visibility into whether their configuration was truly safe over time. This is exactly where endurance simulation comes in. Vector already provided an endurance simulation tool in the past, but it was offered only via support you had to ask for. Users had to send configurations via email and then wait for our feedback. That obviously was slow and inefficient. With NVRAM endurance simulation as a service, this changes fundamentally. The solution is now available as a self-service SaaS application, directly callable from the customer's CI/CD environment. If needed, multiple configurations can be analyzed quickly. Results are generated immediately and detailed endurance reports are provided automatically. This enables much faster iteration, clearer design decisions, and ultimately an optimized flash configuration without waiting for manual support. The NES app is already in productive use by pilot customers via SaaS, so you can already get it. In short, NVRAM endurance simulation as a service brings speed, transparency, and thus confidence to flash configuration. Ah yes, WoDL, this is a big one. Let's first look at how ECUs are typically woken up as of now. In current vehicle architectures, wake-up handling in Ethernet networks usually requires a dedicated hardware support. This is typically done either with a separate wake-up line, meaning an additional cable to each ECU, or with a dedicated CAN network, which is mainly or even exclusively used just to bring ECUs out of sleep. While these approaches work, they introduce additional complexity and in some cases also require extra hardware resources. So naturally, the question is, can we achieve the same functionality without this costly infrastructure? This is exactly where AUTOSAR Wake-up over Dataline, or WoDL, comes in. WoDL allows ECUs to be woken up directly via the Ethernet communication link, without requiring a dedicated wake-up line. The concept is based on the Open Alliance TC10 specification and enables Ethernet transceivers to detect dedicated wake-up patterns directly on the data lane. AUTOSAR focuses on the wake-up aspect only. Full TC10 specification support would also have to include mechanisms for coordinated sleep behavior. But in AUTOSAR, this is left out, as this part is still primarily handled by network management. With release 36, we have introduced the AUTOSAR-compliant integration of the functionality, mainly within the sleep and mode management modules. This includes initial support for selected Ethernet transceivers that already implement WoDL capabilities at hardware level. It is important to note that this is an incremental rollout. The AUTOSAR integration is available, but support is currently limited to specific hardware variants that provide WoDL functionality. Overall, WoDL represents an important step towards simplifying vehicle architectures, reducing dependencies on additional hardware, and enabling more efficient Ethernet-based system designs. I hope you enjoyed this spotlight session on MICROSAR Classic Release 36. The release, including all presented features and more, is already available for you. I want to invite you to check also my videos of previous release spotlights. For example, you might want to learn about the DaVinci Configurator 6, which we already started to write for Release 35 deliveries. Or you want to check again for our new Now QM gateway solution, which I already announced and introduced in Release 34 Spotlight. I'm convinced you could extract at least some valuable information for you. I will be happy to see you again on the next Release 37 Spotlight video. Thank you for your attention.